Hello and welcome to the Mechanics of Materials podcast from Imperial College London. Today we are talking with Dr. Huizhi Wang. Dr. Wang is part of the Electrochemical Science and Engineering group in the Department of Mechanical Engineering here at Imperial College London. She is an electrochemical engineer with a particular focus on the thermal fluid aspects of electrochemical energy devices such as electrolyzers, fuel cells, and batteries. As we move towards further electrification of our world, we need a variety of energy storage solutions to meet our needs. One technology is the electrolyzer. So what are electrolyzers, and how do they fit into the energy storage landscape?
So electrolyzers are devices designed for facilitating the electrolysis processes with a basic principle of using electrical energy to drive a non-spontaneous chemical reaction. In simpler terms, it involves the use of electricity to bring about a chemical change. In the context of renewable energy storage, when you have excess electricity, for example, from the solar panels on a sunny day or wind turbines on a windy day, and you can use that electricity to run an electrolyzer. And if we take a water electrolyzer, for example, then the electrolyzer can use that electricity, otherwise curtailed or wasted, to turn water into hydrogen, which can be stored and later used for power or heat generation or as a chemical feedstock for various industries. And in addition to the water electrolyzers I just mentioned, there are also other types of electrolyzers, for example, carbon dioxide electrolyzers, and they use electricity to convert carbon dioxide into synthetic fuels and valuable chemicals that can be used in the existing infrastructure. They do not only provide a chemical storage solution for renewable electricity, but also help to reduce atmospheric CO2 by closing the carbon cycle. So these electrolysis technologies are collectively termed as power to X, meaning that to convert renewable electricity into more storable form, X. And they can complement other storage technologies such as battery storage, allowing for massive and longer duration storage in the form of chemicals, balancing the seasonal mismatch of energy supply and demand.
Another aspect of your research are fuel cells. So what is a fuel cell and how are they used in conjunction with electrolyzers?
Fuel cells basically reverse the electrolysis process to turn fuels into electricity. Fuel cells, somehow like combustion engines or energy conversion devices that are used to convert the chemical energy stored in fuels into usable form. But they're different from combustion engines in that they use electrochemical reactions to directly convert fuel energy into electrical energy. Therefore, they are not subject to Carnot efficiency limits and often operate at higher efficiencies compared to combustion engines. And if we compare fuel cells with batteries, fuel cells have a rapid refueling time and can generate electricity as long as fuel is supplied. Moreover, fuel cells can decouple the energy storage capacity, which relies on the size of the fuel tank, and power, which relies on the stack size, giving more flexibility in design and applications.
What are some current challenges with the electrolyzer fuel cell system?
The technologies are already there. I would say the most significant challenge hindering their widespread adoption is their costs. The costs can be reduced by multiple ways, for example, by increasing the power density and durability. And we know higher power density usually means that the same amount of power can be achieved with a smaller stack or fewer materials. This can lead to cost savings in terms of materials, manufacturing, and transportation. And longer durability usually means less replacement or maintenance costs. And in the case of electrolyzers, product selectivity also has a big impact on the cost of the process. High selectivity ensures the majority of the electrical energy is used for the intended products rather than being wasted on undesired byproduct or side reactions. High selectivity can also simplify the separation and the purification procedures, leading to cost savings in connection with these steps.
You currently use the field of thermofluid engineering to study these systems. What does it mean to study thermofluid engineering, and what problems are you attempting to tackle with this approach?
As thermofluid engineers, we look into various transport processes involved in electrochemical energy devices, and their interactions with electrochemical reactions. Thermofluid engineering plays an important role in addressing all the challenges I just mentioned. Take the power density of a hydrogen fuel cell, for example. A frequently cited power density target for automotive fuel cells is 9 kilowatts per liter by 2040, as set by the New Energy and Industrial Technology Development Organization in Japan. The European Union Fuel Cells and Hydrogen to Join undertaking set a similar goal of 9.3, but with an earlier deadline of 2024. In comparison, the current state of the art, taking from the second generation Toyota Mirai, stands at 4.4 kilowatt per liter. Achieving the set targets would require significant enhancements in reactant supply, heat removal, and electrical conduction in order to minimize the performance losses. And another key aspect relating to improved power density is water management. As we know, water is one of the byproducts of hydrogen fuel cells. If the fuel cell becomes too dry, it can lead to poor proton conductivity. On the other hand, if there is excessive water, it can flood the electrodes, reducing the available surface area for electrochemical reactions and impeding the flow of reactants and products, resulting in a very fast voltage drop at high current densities. And water management is highly coupled with thermal management, and we know the heat can affect the evaporation and condensation, freezing and melting of water within the fuel cell. So our job is to develop models and innovative engineering designs to engineer these transport processes with a goal to improve the performance of the electrochemical devices. If we take the power density, for example, again, and by using modeling approach, we have demonstrated by simply optimizing the cell structure without shifting to new materials, we can achieve a 46% increase in power density.
The word thermo in thermofluids engineering is quite suggestive when it comes to thermal runaway. As a thermofluid engineer, how do you approach this problem of thermal runaway?
Battery thermal runaway occurs when the isothermic chemical reactions inside the battery are triggered due to the battery temperature rise. For example, the ACI decomposition or decomposition of battery materials. This can lead in a positive feedback loop to intensify the heat generation and further increase the battery temperature. We create models to describe the thermal runaway, initiation and its propagation within a battery pack. By using these models, we can perform virtual experiments, enhancing our understanding of battery thermal safety and reducing the number of expensive safety experiments needed. Furthermore, our model enables the prediction of thermal runaway and its propagation, offering the potential to develop early warning technologies or other safety countermeasures.
Where does the funding for your work come from? Do you have any industrial partnerships?
Our funding comes from EPSRC, Faraday Institution, and Innovate UK, and we collaborate with industrial partners spanning various sectors such as energy, automotive, aerospace, and chemical manufacturing.
Well, Huizhi, thank you very much for talking with us today.